Um, yeah. So last time we talked about this. So the picture that we. One minute, just a minute. Last time we had talked about an isolated system. So the system is isolated. And it contained in particles in volume V with energy between E and E plus delta. So we were considering the equilibrium state of the system. So this is okay, it's feasible, right?
Yes, sir.
Equilibrium state of the system, and we said that the equilibrium state of the system has this space-based distribution. This is equal to 1 divided by gamma of NVE. If the microstate has the right energy, that is E less than h of PIQI less than E plus delta, and is equal to 0 otherwise. Where we have defined this quantity gamma to be the number of consistent microstates, number of microstates that make up the microcanonical ensemble. So it's then we said that once we know this quantity, then I can reproduce the whole of thermodynamics by just identifying that my entropy, which is NVE, function of NVE, is just KB log of this gamma function up to an additive constant. And once I know the entropy, then everything is defined because the temperature is given by okay, before temperature, the first thing is the energy, internal energy. The internal energy is nothing but E itself. Temperature is given by the derivative of entropy with respect to energy. Pressure is given by temperature is given by the derivative of entropy with respect to volume. And then everything is well defined. So what I would like to do today is to tell you how this formalism can be used to derive the ideal gas. Okay, so then that would mean that this formalism is consistent with existing experimental facts. It doesn't violate any one of them. At least it doesn't violate the ideal gas law. So therefore, it makes sense to use this formalism to try to derive the ideal gas law. PV is equal to NKV. That's what we are going to do today, in the first part of the lesson. So before that, there is a small comment. Which concerns this entropy function, which is the following. that we have defined this space of NVE to be KB log of gamma NVE, where gamma NVE was this integral. This integral I can write it as sigma of NVE plus delta minus sigma of NVE. So this you can recognize this is nothing but the phase space volume uh, corresponding to the region between two hypersurfaces, one corresponding to the energy E and the other corresponding to the energy E plus delta. While sigma, it is just the phase space volume with energy less than E. So this is defined to be this guy. This is obvious. I mean, the relationship between the two, that is obvious. But the thing is that since delta is much smaller than E, so therefore I can do a Taylor expansion. So the leading term will cancel and I will be left with what? I will be left with delta times del sigma del E. So this is another way to express gamma. And it turns out that you use either this definition or you use KB log of sigma NVE. You will get basically same answer. I mean, there will be some corrections of order which are subleading in the number of particles. So therefore, we have a choice. Either you use gamma in computing the entropy or you use sigma in computing the entropy. You will get the same answer to leading order in the number of particles, and which is what we want. We don't want any subleading correction because anyways n is a very large number, 10 to the 23. So therefore, it suffices to keep the leading order term, and it also suffices to neglect the next order term, which is precisely what we will do. So therefore, depending on circumstances, it may be possible to evaluate one or the other more simply, and whichever is the simpler of the two, we will just adopt that. Turns out for ideal gas, I mean, you can work with this one. This is more simple to compute. You can also use this one. Either way, it's good enough. So let's just do the calculation for an ideal gas. So first, let us define what is an ideal gas. So an ideal gas is any gas at very high temperature or low density. What happens is that if you take any gas and you heat it up to very high temperature, then what happens is that the kinetic energy term in the energy will dominate over the potential energy term. So to a good accuracy, you can neglect the interactions between the particles making up the gas molecules or the gas particles. So therefore, ideal gas is one in which, if I write down the Hamiltonian, it's just composed of the kinetic energy contribution. The potential energy contribution is negligible simply because I have heated up the gas to very high temperature. Okay? So that's the definition of an ideal gas. You take any gas, you heat it up to very high temperature, whatever you get is called the ideal gas. So this is the Hamiltonian. So once I know the Hamiltonian, now the next thing will be to compute sigma and then entropy and temperature and pressure and show that you get the ideal gas. So let's just try to do that calculation. Okay. So the first thing to do is write down the definition of sigma. You have the definition. H, I know what is the form of H. So let's just write this. H is this. See that in H there is no contribution of Q. So therefore the Q part can be integrated out easily because the Hamiltonian doesn't depend on the coordinate. So the coordinate part in the integral can be evaluated quite easily. So for every particle there are three Qs. The Q in the X direction, the Q in the Y direction, and the Q in the Z direction. These three will give me one volume factor, and there are n number of particles. So therefore I will get V to the power n as the volume factor. So this is trivially equal to V to the power n times the rest of it remains as it is. So I need to integrate this factor, this thing, the integral, and see what I get. And I should be getting the ideal gas law at the end of the day. Okay. So if I look at this integral, it looks like in the 3n dimensional momentum space, this is going to give me the total volume of a sphere with radius equal to square root of 2me. Okay, so this is nothing but in the 3n dimensional momentum space P1, P2, P3, all the way up to P3, and this is nothing but the total volume of a sphere whose radius is equal to square root of 2m. Why this is so? This is because of the form of the Hamiltonian. So the summation over I1 to 3 and pi square, that gives me just the square of the length of a vector in this 3n dimensional space, and what it says is that the length of the vector squared should be 2me, and therefore the length itself should be square root of 2m. So I just need to know what is the volume of a 3n dimensional sphere of radius r. I need to have a formula for that. So let me denote this by as omega 3n. This is the volume in a 3n dimensional space of a sphere with radius square root of 2me. So I just need to find this factor. Once I'm done with it, then I can just substitute it and then take the derivative and so on. Okay. So let's first find out what is the volume of a sphere in an n-dimensional space whose radius is r. So some formula we know. For example, if you are in one dimension and you want to know the volume of a sphere of radius r, in one dimension a sphere becomes just a line, straight line, because you don't have the other directions, you just have one direction. So therefore, in one dimension, this will be nothing but 2r. So you take a sphere, you project it onto two dimension, you get a circle. You project it onto one dimension, you get a line. The line will be just the diameter of that circle. This we know. When you are in two dimension, then we know what is the volume of a sphere of radius r. In two dimension, the volume of a sphere of radius r, it is just the total area of a circle of radius r. So that is pi r square. And in three dimension, we know how it looks like. So it is 4/3 pi r cube. But we want the answer for general value of n. N. Suppose I give you n equal to 56, what is the answer? How does it look like? So this is something that we need to figure out. And once I do that, then I'm fine. So let's just try to do this. Keep this in mind that this sigma is nothing but v to the power n omega 3n of square root of 2m. That what I need to do is to first realize that omega n of r, it could be r to the power n times some constant. Why? Because in one dimension it is proportional to r, in two dimension it is proportional to r square, in three dimension it is proportional to r cube. So therefore in n dimension it will be proportional to r to the power n with some numerical factor in front which we need to find out. We know what the factor is in one dimension, it is 2, in two dimension it is pi, and in three dimension it is 4/3 pi. So therefore we need to just find out how does it look like in any arbitrary dimension n. So to do that, we need to do some mathematical jugglery, some play with some integral and this and that. So let's just try to do it. So what you do is, you first consider this identity. dx1, dx2, dxn of e to the power minus x1 square plus x2 square plus blah 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 xn square. This is an unconstrained integral. All the x's are independent of each other, and we know this answer for a Gaussian function, this Gaussian integral, minus infinity plus infinity of e to the power minus a x square plus bx dx. You can look up standard integral table, or this is very easy to do this integral by doing a transformation and converting it into an integral that involves converting it into an answer that involves a gamma function. So this would be just square root of pi by a e to the power b square by 4a. So I just use this here. There are n such integrals, n number of such integrals, and each integral you just put b equal to 0 and a equal to 1. So therefore you get square root of pi, and there are n such integrals, so therefore you get square root of pi to the power n, which is pi to the power n by 2. But then I can do this integral in another way. Okay, what I can do is that I can convert it into, just as in, let's say, in 2 dimension, you have to do an integral dx dy. You can convert it into polar coordinates. You can go from x, y to r theta. Okay, so I'll do the same thing here. So I can write this integral as, see, this dx1, dx2, dxn, this is by definition a volume element in this n-dimensional space. So this would be just d omega n of e to the power minus r square, where r is a vector in this n-dimensional space whose length is square root of x1 square plus x2 square plus xn square. But a volume element can be converted into a volume integral can be converted into a surface integral. So what I do is that d omega n, I can write it as 0 to infinity of dr snr. This I can always do because this is the volume element. So I can write it as how do I construct a volume element? So what I do is that I first find what is the surface area and then integrate in the radial direction. So dr snr e to the power minus r square. Okay. What is this snr? snr. So snr dr is equal to d omega n r, which implies snr is by definition the derivative of the volume element with respect to r. And I know how the omega in r goes as a function of r. So if I just take the derivative, I get ncn r to the power n minus 1. Here I just take the derivative with respect to r. I get ncn r to the power n minus 1. So I just plug it in here. I get ncn r to the power n minus 1 e to the power minus r squared dr 0 to infinity. But this one is quite easy to evaluate. You convert it into an integral that involves a. So what you need to do is, can somebody tell me what I need to do to evaluate the class integral? How many of you have seen such an integral? Nothing to do with statistical mechanics, I mean, just mathematical physics thing.
The gamma integral, sir.
Yeah, gamma integral, and then I cannot write directly this as a gamma integral because I need to do something. I need to do a transformation. R square I put equal to y, right? Because gamma function is what? The definition of gamma function is that could be what, x to the power n minus 1 e to the power minus x dx. So here this factor, r square factor has to be made linear. So what you do is that you define you do a transformation of variable r square equal to y, and dr is equal to therefore 2 dr, 2r dr and so on. Okay, so it's just a one line calculation. Okay. this integral can be done quite easily. So if you do this, then what you get is this one is nothing but NCN gamma of n by 2. So therefore, I have done this integral, evaluated this integral in two different ways. One is to evaluate it as product of n independent integrals. Then the answer that I get is pi to the power n by 2. The other one is to write it as, in terms of these coordinates like r and SNR and so on. And then I get NCN gamma n by 2. So therefore, the two sides have to be equal. So therefore, I get an equality, which is what? Which is NCN gamma n by 2. The factor here has to be equal to the factor there. So this fixes the value of Cn. Okay, so Cn will be pi to the power n by 2 divided by n gamma n by 2. So I just substitute it here. To get r to the power n and Cn is pi to the power n by 2 divided by n gamma n by 2. But n gamma n is nothing but gamma n plus 1. So this is a property of the gamma function. So therefore I get this as r to the power n pi to the power n by 2 by gamma n by 2 plus 1. Okay. So therefore I know how does this function look like. So let's just substitute that there. So this factor we have now found out. And 4 to the power n by 2. Sorry, 3n by 2 because there is 3n by 2 and then pi to the power 3n by 2 divided by gamma of 3n by 2 plus 1. So this is the final answer for sigma. Okay. So once I know sigma, then I need to find what is the entropy. Now we have to use that. Okay, by the way, I can write this gamma of 3n by 2 plus 1. That is just gamma n n minus 1 factorial. Now n is very large, so therefore I can use the Stirling approximation. The Stirling approximation, it says log of n factorial is equal to n log n minus n plus some leading terms in it that we can get rid of. So what I have to do is that I have to take this expression, take the log of it, and then use this approximation. So it's a bit of an algebra, but very straightforward algebra, no big deal. So finally, what you would get at the end of the day is an answer of this sort. this would come out to be yeah, would come out to be n kb log of v into 4 pi m by 3 e by n whole to the power 3 by 2 plus 3 by 2 n kb. So this is very straightforward. So what you do is that you take this expression, take the log of it. Okay, you know how to evaluate log of a function and use this approximation. So this is the expression that you would get. So now what is the next thing to do? I have to find the temperature. Temperature is what? Temperature is I have to take the derivative with respect to E. If you take the derivative with respect to E, it is quite easy to do. Log meaning you will get this factor in the denominator, and in the numerator you will get what? You will get 3 by 2 e to the power half. So if you do those cancellations, you will come out with this expression. This will be just 3 nkb divided by 2e. Similarly, you can find the expression for the pressure by temperature, and you will find that pressure by temperature will just come out to be n kb. How do you get pressure by temperature? So you have to do this integral. Pressure by temperature is basically del S del V. Okay, so you have to just take the derivative with respect to V. And if you do that and use this expression, you will get this to be equal to just n, which implies that we have been able to, n kb by V. Sorry. Why you get a V in the denominator? Because when you take the derivative of this function with respect to V, because of this log function, this whole factor will come in the denominator. That's why you get a factor of V. So therefore, if I just combine these two, I get the ideal gas law. PV is equal to NKV. Okay. So therefore, using the statistical mechanics, we have been able to derive the ideal gas law, namely that PV is equal to NKVT. We did not do many assumptions, excepting that we invoke this phase space picture. The phase space picture has to do with the fact that you first enumerate all the consistent microstates of the system, and then you say that these microstates are distributed in the phase space in a particular manner. And what is that manner? Well, the microstates are all uniformly distributed in the phase space, and that led to a phase space density in the microcanonical ensemble that's uniform. And from the normalization of the phase space density, we fixed that uniform density to be equal to 1 over gamma, where gamma is the total number of consistent microstates making up the microcanonical ensemble. And once I know gamma and sigma, then the next thing would be to define the entropy of the system, which is just kb log of that factor gamma or sigma, it doesn't matter really. And once I know the entropy, then the rest of the journey is rather simple. I have to just take the derivative of entropy with respect to energy. In doing so, I get the temperature. I take the derivative of the entropy with respect to volume, I get pressure, and that's it. And then I use this exercise, I employ this formalism to now derive the ideal gas law. So everything is consistent and everything is, you are getting answers which are consistent with one another. So microcanonical ensemble is a very good description. Microcanonical equilibrium is a very good description of a system which is isolated. Okay, so I think now I will move on to canonical ensemble. But before I do that, let me take a pause for maybe 2-3 minutes and wait for you to know if you have questions or queries, if you want something to go over, uh, that you want me to go over again and so on. Otherwise, I'll move on to the canonical ensemble. Yeah, the questions I'm just waiting for you.
No questions, sir.
Then the next thing would be to continue to the canonical ensemble, uh, which is the next level of um, complication that we will deal with. And like as it will turn out, I mean the canonical ensemble calculation turns out to be simpler than the microcanonical one. For the following reason that we saw that the sigma or gamma, these are the important quantities that one has to compute in order to do any progress within the microcanonical ensemble. But these are high dimensional integrals involving constraints. For example, gamma involves the constraint that you have to consider only those microstates that have energy between E and E plus delta, while sigma involved those microstates that have energy less than a given number E. So these are constrained integrals. So therefore, microeconomical ensemble, though well defined as it is a rather difficult thing to deal with analytically. If you want to compute something, make some progress, you have to deal with high dimensional integrals. For the ideal gas case, it became simpler, simply because in the kinetic, in the expression for the Hamiltonian, you did not have any contribution from the potential energy. So therefore, the coordinate part could be integrated out rather easily. But in a typical system, there will be interactions and the Hamiltonian will be composed of both kinetic and potential energy contributions, and therefore doing this integral will not be an easy task. So therefore, what you do is that you make life simple, you go to another ensemble which is known as the canonical ensemble, which turns out, as we will see now, which turns out to be less constrained than the microcanonical ensemble. So let's just see how does one go about doing that. For the canonical ensemble, microcanonical ensemble setting, we had a very big system with energy and volume and number of particles given like this. Okay? And the system, of course, conserves the total energy. Okay? Now, what you will do is that you ask, what about a subsystem of this system? If I consider one subsystem of this system and ask for its phase space distribution, let me call it subsystem 1 and subsystem 2. If I ask for the phase space distribution of subsystem 1, that is to say, rho of P1, Q1, what does it look like? Okay. So the subsystem 1 that has got N1 particles with volume V1 and some energy E1, and subsystem 2 will have N2 particles with volume V2 and some energy E2. But these are quantities that satisfy these equalities, that N1 plus N2 is equal to N. Also, N1, N2, these are constants. Why? Because I'm considering a subpart of this system, but the subpart is very special in the sense that the boundary here, it allows only energy exchange. So this boundary doesn't allow particles to move back and forth. The boundary is also rigid in the sense that it is not vibrating. So it doesn't allow particles to be exchanged, it doesn't allow volume to be exchanged, but then it does allow energy to be exchanged. Okay? So therefore, I wrote N1 plus N2 equal to N and N1 N2 are individually constant. Similarly, V1 plus V2 is equal to V, and also V1, V2, these are constants. But then when it comes to energy, then of course, E1 plus E2, which is the energy of system 1 plus system 2, that lies between E and E plus delta. But as opposed to these quantities, E1 and E2, they are not constants. Why? Because the two subsystems can exchange energy among themselves. So therefore, these quantities are individually not constants. Now, when I wrote down this equation, I made an approximation. So let me just mention what is it. So if I have a system and if I consider a subpart of it, then let's say call it system 1 and system 2, then the total energy of the system is equal to the energy of subpart 1 plus energy of subpart 2 plus there will be a cross term. Why does this come into being? It comes into being simply because you may have potential energy contribution coming from particles, pair of particles, one of which is here and one of which is there. So this is what is known as the the interaction between system one and system two. But what I am assuming here is that both systems one and two are short range interacting. What do I mean by short range interaction? It just means that every particle is interacting with other particles which are contained in its close neighborhood. It doesn't, the particle doesn't interact with particles which are very far off. It interacts only with particles which are in its close neighborhood. And so therefore, in this case, this E12, this will be proportional to the surface area of the bounding partition. Okay, so this will be a surface term. Surface term. While these numbers, they are proportional to the total number of particles contained in the system. Okay, and the total number of particles contained in a given volume is proportional to the volume. If I assume a fixed density of particles, then as I increase the number of particles, I have also to proportionately increase the volume of the system. So therefore, these quantities, these are proportional to the volume. So therefore, when you make system 1 and system 2 larger and larger, the surface term will be a negligible correction. Surface term will be dominated over by the volume term. So therefore, I can neglect the surface term. Which is precisely what I have done in writing down this equation. So therefore, whatever I say now about canonical ensemble will apply to a system that is composed of particles that are short range interacting. Simply put, short range interaction means that every particle can interact with other particles which are in its close neighborhood. Let's take an example of an interaction which is not short range. Gravitational interactions are not short range. Coulomb interactions are not short range. So therefore, for these systems, this formalism will not apply, but it will apply to other systems for which the interaction is short range, nearest neighbor interaction, exponentially falling off interaction, and so on. Okay. Uh, so this is the setting. Now I did a change of notation here. So let me just explain. When I write P1, Q1, what I mean is basically P of where I did, P in one coordinate values and 3 into momenta values of particles in one. So this is a shorthand notation. It doesn't mean first particle or anything of that sort. It just means this is the collection of numbers defining the coordinates and momenta of all the 3 and 1 particles which are in system 1, subsystem 1. Similarly, P2Q2 would mean the coordinates and the momenta of all the particles making up subsystem 2. Okay. And our question is, what is this one? Given that for the entire system, the equilibrium phase space density, which will now be a function of P1, Q1, P2, Q2, for the equilibrium of the entire system, I have the microcanonical sum. So therefore, I am asking the following question that I have a big system the system itself is in microcanonical equilibrium, and I look at a subpart of it, which is also quite big. And the question that I am asking is, what is the equilibrium phase space distribution of this subpart, given that the entire system is in microcanonical equilibrium? There's one more notion that I need before I go on. Since the entire system is in equilibrium, so therefore I know that every subpart of it will be at the same temperature. Okay, so therefore, if I measure the temperature of system 1 and measure the temperature of system 2, I'm going to get the same value of the temperature. So I need to keep that in mind also. I also need to keep in mind the pressure is also going to be the same everywhere. With that background, let us just try to find out this knowing this one. E1 Q1, let me write it 1. 1 meaning that I am interested in the free space distribution of system 1. Okay. So how does it look like? So this would be proportional to, so this is in equilibrium. Okay. This would be proportional to, I take the equilibrium distribution of the full system, I integrate out the P2s and the Q2s. And remember that these are not like two-dimensional integers. These are instead 6 into number of, there are 6 into number of variables there. So this is just a shorthand notation. It means that you need to integrate over the momenta, all the momenta values corresponding to system 2, all the coordinate values corresponding to system 2. I integrate over all such values, keeping this in mind that if system 1 is in this microstate, then the corresponding energy will be E1 and therefore E2, because of energy conservation, will have energy lying between E minus E1 and E minus E1 plus delta. Okay. So now let us try to evaluate this quantity. This quantity I know is given by this, so therefore I just substitute it there. Will be 1 divided by gamma of NVE of this integral. E minus E1 less than h of P2 Q2 less than E minus E1 plus delta of dP2 dQ2. But this integral we already know what it is. This integral by definition is nothing but gamma of n minus n1 for system 2, that many particles are there in this volume and the energy is E minus E1. Okay. So therefore, what I get is the quantity that we were after is given up to some constant by the ratio of gamma of n minus n1, p minus p1, p minus p1 divided by gamma of n v. How I mean for an assumption, which is a very realistic assumption to do, which is that system one itself, a big system, is much smaller than system. So what is the physical picture that I have in mind? The physical picture that I have in mind is that of a system which is interacting, exchanging energy with the universe. Okay? But the system plus universe is isolated and it is in microcanonical equilibrium. But the system itself is not isolated, it is continuously exchanging energy with the universe, and everything, system plus universe, is isolated. So therefore, since one is the system that we are interested in, and two is supposed to represent the universe, it is a reasonable thing to assume that N1 is much larger than N2, V1 is much larger than V2, and E1 is much larger than E2. So since the total energy is nothing but the sum of energies of the two subparts because of this one. Sorry, E1 is, I did it the other way around. N1 is much smaller than N2 because this is just a small part. V1 is much smaller than V2 and E1 is much smaller than E2. So therefore, if I look at the total energy, which is sum of energies of E1 plus E2, but E1 is much smaller than E2, so therefore this is to a very good approximation equal to E2. So therefore, let me come back to this expression, and since N1 is much smaller than N2 and so on, so therefore I can do a Taylor expansion. Remember that N is equal to N1 plus N2, V is equal to V1 plus V2 and so on. So if I do a Taylor expansion, of course, this vector will just come out. But before I do a Taylor expansion, let me do a small, take a small step, a mathematical step, which is that I know S is equal to KB log gamma. So therefore, gamma will be nothing but e to the power S by KB. So I use it here to first write this as e to the power S by KB of n minus n1, b minus b1, e minus e1. Okay. And now I do the Taylor expansion. Okay. So if I do the Taylor expansion, of course I will have a factor gamma in VE remaining as it is. And here what I would get, I would get e to the power S by KB of NVE minus E1 del S del E1 by KB minus V1 by KB del S del V minus N1 by KB del S del N. So if I have to know, so let us first find out, you see these things, N1, V1, these are given numbers. So therefore, these derivatives, these two derivatives, they will give me some constants. Okay? They will not change if I change the microstate. Why? If I change the microstate of system 1, they will all correspond to the same number of particles and same volume. So therefore, these are quantities that can be treated as constant. They don't change when I change the microstate. This term doesn't change when I change the microstate. This term doesn't change when I change the microstate. This term doesn't change when I change the microstate. But this term does change when I change the microstate of system 1. Why? Because if I change the microstate of system 1, the energy of system 1 changes. And E1 is nothing but the energy of system 1. So therefore, the remaining factors I can write as some constants, constant times e to the power minus e1 by kb del s del E. Or what is del s del E? Del s del E, we know what it is. It is the inverse temperature because we had this definition that 1 by T is equal to del s del E. So therefore, del s del E is 1 over T, I get this answer. E1 by kb. So after doing all these things, the final answer that I have is this quantity is proportional to the power E1 by kb. But E1 is what? E1 is the energy corresponding to this microstate. So therefore, this is same as e to the power minus h of P1 Q1 divided by kb. How do I, so there is a constant factor here, let me take it be like this constant. How do I fix the value of the constant? By invoking normalization. Because this is the phase space density of system 1, exchanging energy with system 2. So therefore, I can invoke the normalization of rho 1 to fix the value of the constant. And if I do so, I will want this constant. One. So this gives me A to be equal to 1 divided by e to the power minus h of P1 Q1 by KBT P1 dQ1. Okay, so this is the normalization constant. So if I now plug this in here, I get to be this to be equal to e to the power h of P1 Q1 by KBT divided by this integral dp1 dq1 e to the power minus h p1 q1 by kbt. So therefore, we have been able to obtain what is known as the canonical equilibrium answer, which is the following: that if I have a system which is in contact with the universe and exchanging energy with the universe and is in equilibrium with the universe and is at a constant temperature T, and if I ask what is the phase space density of this system that has the formula rho Q is equal to e to the power minus h dq by kbt divided by z. What is this z? Z is this integral, the normalization constant, inverse of the normalization constant, dp dq e to the power minus h pq by kbt. And this z has a name, it is called the canonical partition function. Now what do I do? Yeah, how do I make connection with thermodynamics? See, we have to make connection with thermodynamics. In the microcanonical ensemble, when the system was isolated, we were obliged to compute the gamma factor and then take the log of it and multiply by Kb to get what is known as the entropy of the system. Here also, I need to do something. And what I need to do is I need to take the log of this z. First of all, let us find out what is z a function of. Z is a function of course, the number of particles, the volume, and the temperature. The things which are constant. So I just take the log of it, but then here I have to multiply by kBt and put a minus sign, and this gives me what is known as the Helmholtz free energy of the system. We will in the next class derive some expressions for this free energy to see how does it connect in with thermodynamics. But at least in the canonical ensemble, this is how you define the free energy of the system. In the next class, we will see what is the utility of the free energy, why would somebody like to define the free energy, and what are its implications for thermodynamic quantities. But this is how the free energy is to be computed within the microcanonical ensemble. Okay, so are there questions?
Sir,
Yeah.
partition function is dimensionless or not?
Partition function is dimensionless. Yes.
Sir, in the canonical partition function, the 1 by h is missing.
What is missing?
1 by h.
1 by x.
Planck's constant.
No, this Planck's constant, you see, that is the thing that I don't like. You see, this Planck's constant, it doesn't appear in classical statistical mechanics. Okay. So what you can do is that, see, ultimately what you do is you will have to take the derivative of this free energy. Okay? So what you can do is that to make this dimensionless, you can multiply by some number, let me call it A. Okay? Some number, it will appear only as a, some constant here. It doesn't have to be Planck's constant. It is some number that has the dimension, that it has the right dimension to make this quantity dimensionless. But you see, this is just an additive constant. And ultimately, you have to take the derivative of the free energy with respect to nVt. And when you take the derivative, this constant is inconsequential. Just as it is the same thing that you had for the entropy, that AC is equal to Kb log omega plus a constant. But that constant I don't care, because anyways entropy I will not be able to measure in experiments. I can only measure the derivative of the entropy with respect to temperature, volume, etc. Here also, I will do the same. I will take the derivative of free energy with respect to nVt. And when I do the derivative, then this factor is inconsequential. Okay?
Okay, sir.
So that factor you can put it to be Planck's constant or whatever, like anything that has the dimension of Planck's constant. Why that Planck's constant factor is put in traditionally is, you see, this integral, this will involve a PQ, and how many such PQ factors will be there? There will be PQ to the power 3n. That many factors are there. And PQ has the dimension of h bar. That's why you put h bar to the power 3n. But in principle, you can put any number, any number here with the right, any constant, any factor here with the right dimension. But then when you take the log, this will come out as an additive constant. Some factor will come out, which I don't care. maybe there is a minus kVt, but like again, these are constants. Okay.
Okay, sir.
Yeah, what I'm thinking is, should I do the, so how much time is left? Can you tell me? Maybe 10 minutes, huh? Okay, so maybe I just tell you what is the utility of the field. For that, one is to go back to the Clausius's inequality. Or what the Clausius's inequality was. So we have written it like this: E plus Q by T. In any thermodynamic transformation from A to B that is quasi-static, you compute this quantity. So this quantity was less than equal to Sp minus S. Where the inequality was for an irreversible transformation, and this one was for a reversible transformation. But suppose this transformation takes place in such a manner that temperature remains a constant. Okay, so you are starting with the system in equilibrium, and then you are making the system undergo a transformation quasi-statically from one state, equilibrium state, to another. But during the whole process of transformation, temperature remains a constant. Suppose I do such an experiment. It is quite easy to do such an experiment. To keep the temperature constant, what I have to do is to keep the system in contact with the heat path, that is a reservoir, or let's say a burner or an oven that maintains it at a constant temperature. So if temperature is constant, I can pull this 1 by T factor out. So what I will get is 1 by T of T cross Q less than equal to T of Sp minus S. Or delta Q is less than equal to T delta S. Okay. But what is delta Q? Delta Q is equal to delta U plus P delta V. Or more precisely, delta Q is equal to delta U plus delta W. So I just substitute it here. What I get is delta U plus delta W is less than equal to P delta S, or delta U minus P delta S is less than equal to delta W. Now I define a new quantity, F, which I call it U minus Ts. This is the definition. Why do I define it? Because if I now compute delta F, I know that in this transformation temperature is a constant. So if I do this, I will get, but since temperature is a constant, this term is. So I just substitute it here. I get delta F is less than equal to delta W. So what? What is the utility of it? So what it tells me is the following. So delta W, recall, is the work done by the system. Okay. So what I do is that I suppose I want to make this work done on the system. So work done on the system will be negative of the work done by the system. So therefore, if I just invert it, I will get this relation, work done. Okay, let me not do it then. Okay, let me do it this way. So this is what you get. Now, how will work be done? Think of the canonical ensemble setting. Work will be done when the volume of the system changes. But in the canonical equilibrium setting that we discussed, the volume of the system doesn't change. The system is allowed to only exchange energy with the rest of the universe. It doesn't change its volume, it doesn't change its particle number. So therefore, no work can be done on the system or no work can be done by the system. So therefore, the right hand side is 0. Okay. So therefore, what I get is delta F is less than equal to 0. That is the quantity F. What is that quantity F? We called it the Helmholtz free energy. So when a system is in canonical equilibrium, and if it undergoes thermodynamic transformation from one state to another, the change in the Helmholtz free energy of the system is always negative. Okay, that is to say that under any transformation that a system in canonical equilibrium undergoes, the free energy of the system can only decrease. It can never increase. So what is the utility of the Helmholtz free energy? The utility is the following, that if you want to know the equilibrium state of a system in canonical equilibrium, then what you need to do is just to minimize the free energy of the system. Why? Because when you are changing, when you let the system undergo some thermodynamic transformation, the free energy only decreases, but then it can no longer decrease if it hits its minimum. So therefore, for a system in canonical equilibrium, the equilibrium state is the one that minimizes the Helmholtz free energy. So that is the utility of the Helmholtz free energy. That it describes the equilibrium state of a system which is mechanically isolated, that is no work can be done on the system or by the system, and the system is in contact with a heat bath, therefore it is at a constant temperature. So that is the utility of the free energy, Helmholtz free. And we know how to compute it in the canonical ensemble. You need to know the canonical partition function, take the log of it, multiply by minus kVt to get the free energy of the system. Okay. So maybe I should stop here and ask for questions if you have some questions. Please feel free to ask questions because otherwise I will not know.
Hello, sir.
Yeah.
Praveen here.
Yeah.
Just for curiosity, I'm asking this question.
Yeah.
Can we relate this Helmholtz free energy to the entropy and second law of thermodynamics?
Yes, yes, of course. So this is the thing. Now, F is related to entropy this way.
F is equal to U minus Ts.
Yeah. And in the second law of thermodynamics, we have TTS is equal to TU plus TdV. But what is TDS? TDS, actually TU minus, okay. So you will get exactly this relationship. Why? Because sorry, I messed up a minus. So TDS is equal to TU plus PdV. But what is dF? dF is equal to du minus TDS. So du minus TDS is dF and minus PdV is equal to du. Yes, did I do it? Yes. Fine. So this is exactly the equation that I have written. The less than comes when you have the transformation as an irreversible transformation. Or df is equal to minus PdV, which is nothing but minus dw, which is exactly what I have here. Okay.
Okay, sir. Thank you.
Are there other questions?
No questions, sir.
Okay, so then maybe we meet again at 1:30 p.m. Right? I mean, 1:30 is the time here. So if you have questions, then keep them in your mind, and when we come back in the afternoon, you can ask me. Okay.